Hello and welcome to this Bioprocess International Ask the Expert webcast. I'm your host, Alex Nicolaitis, the webcast coordinator for Bioprocess International. Before we get started, just a couple of notes. This webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the question and answer window on your screen. After the presentation, we'll begin the Q&A portion and I'll ask our speaker your questions. Your questions in the Q&A window will only be visible to myself and our speaker. So thank you for joining us today. It's now my pleasure to introduce our speaker, Julia Hanks, PhD External Collaborations Manager, Cell Culture Technologies from Sartorius.
Thanks for the kind introduction, and as already mentioned, today I'm looking forward to share updates from a collaboration with the University College London about the topic optimizing perfusion parameters for intensified production of CAR T cells in the AMBER 250 high-throughput bioreactor. Before diving into the results of this new intensified process, I like to emphasize the key challenges of autologous engineered cell manufacturing. Besides some of the key challenges, high costs of manufacturing, high and unsustainable production failure rates, long vein-to-vein processes, as well as lengthy quality control and product release. Furthermore, both the logistics of individualized products and the supply chain management are complex. To overcome those challenges, we observe new trends in the CAR T cell field, such as in vivo CAR T cell therapy, new generation CAR constructs to improve the potency, and allogenic approaches, as well as intensification of the manufacturing process to allow off-the-shelf availability at much lower price. This requires scalable automated bioreactor systems with small-scale models that are applied for screening and process development and allow for seamless transition to robust manufacturing platforms in large scale. With our fully automated stir tank bioreactors, we allow for monitoring and control of process parameters such as pH, dissolved oxygen, and agitation. And we have proven scalability and offer a range of bioreactor systems from the milliliter scale up to 2,000 liters. As these stir tank bioreactors have been used for decades for biologics production, and thus the fluid dynamics and engineering considerations are well characterized. In the CAR T field, there is a fundamental need for process development and optimization at small scale, minimizing the cost of goods. Therefore, we investigated whether CAR T cells can be grown in stir tank bioreactors. We decided to use the AMBER 250 modular for initial experiments and address the research questions whether CAR T cells can be cultured sufficiently in stir tank bioreactors, and which process parameters impact on the CAR T cell quality and functionality. In the next step, we employed a quality by design approach to investigate whether process intensification in the AMBER 250 high throughput is beneficial for the CAR T cell growth kinetics and can lead to reduction of the process time. However, the first research question we addressed was whether CAR T cells can be expanded in stir tank bioreactors. To address this, primary T cells were isolated, activated with Dynabeads, transduced with lentivirus, and 7 days pre-expanded in T-flasks. Then the CAR T cells were transferred into the AMBER 250 that was used with the unbaffled AMBER 250 vessels that only has one large pitch blade impeller to allow gentle agitation. The CAR T cells were expanded for 7 days at 5 different steering speeds, ranging from 100 to 500 RPM. As comparison, CAR T cells were cultured in static culture in flasks, which is illustrated as black lines. The top lines show the viability, which is between 90 to 100% for all conditions. The other lines show the number of viable CAR T cells over time. The arrows indicate media addition or exchange during the fed batch process. This plot nicely shows that CAR T cells expand well in the AMBER 250, and the final cell yield achieved upon the 7-day culture is even higher than in the static condition. Moreover, this plot illustrates that steering speed, upon reaching a minimum of 200 RPM, does not negatively impact the CAR T cell growth. The fold expansion for each condition is summarized in the upper right plot. This data confirms that CAR T cells expand better in the AMBER 250 than in the flasks, especially with a steering speed between 200 to 500 RPM. This is important as large-scale bioreactors, especially relevant for allergenic approaches, might require even higher steering speeds. Furthermore, the CAR expression was neither affected by the culture system, static culture or steering, nor by the steering speed. Based on this proof of concept data that was generated in collaboration with Qasim Rafiq, professor at UCL, and Elena Costariol, PhD student in Qasim's lab, we aim to investigate how adapting the process parameters affect the CAR T cell growth kinetics and their phenotype. Therefore, the next research question that we addressed was whether we can shorten the time of the process. To do so, we shortened the pre-expansion phase, which has been 7 days for the data shared so far. However, this was investigated first in static culture in flasks. Here is the process based on the 7-day seed train depicted. This includes 2 activations at day 1 and day 9. The question we asked was whether CAR T cells grow well after only 3 days of pre-expansion and a single activation at day 1. The results from the 7-day pre-expansion process will be presented in gray, and the results from the 3-day pre-expansion process will be presented in light blue throughout the following slides, focusing on this comparison. Interestingly, CAR T cells that are pre-expanded for 3 days only are growing better during the 7-day culture in the flasks and reach a higher fold expansion. To further characterize the CAR T cells, they were phenotypically analyzed by flow cytometry to, on the one hand, identify the differentiation stage based on the CD45RO and CCR7 expression. The shorter pre-expansion process resulted in a CAR T cell population with less differentiated cells, meaning an increased frequency of naive and central memory CAR T cells. This is of relevance as it has been shown that especially the less differentiated CAR T cells have a better longevity in vivo. On the other hand, the expression of activation and exhaustion markers was analyzed. Here, the 3-day pre-expansion process resulted in lower CD69 or PD-1 and LAG3 expression levels. This is beneficial as the CAR T cells are less activated and less exhausted upon 7-day culture. In addition to this phenotypic analysis, it is important to prove that the CAR T cells are functional and thus able to kill target cells in a specific manner. The specific killing capacity of the CAR T cells post-expansion was analyzed through quantitative live-cell imaging with the IncuCyte. Therefore, CAR T cells were exposed to target GFP-positive NALM-6 cells. As control, NALM-6 cells were cultured alone, and as shown in black, they grew constantly over the observed duration of 45 hours. The dotted lines show target cells that were co-cultured with non-transduced T cells. Some unspecific target cell killing is observed. However, the NALM-6 cells still expand over time. Most important, the continuous lines show target cells that were co-cultured with CAR T cells. As these cells are able to specifically recognize the NALM-6 cells via the CAR, the target cells are efficiently killed in this condition. In addition, the cytokines secreted by the CAR T cells upon the killing assay can be measured. The secretion of interferon gamma and TNF alpha was measured upon the co-culture of CAR T cells and target cells with IQ-Q beads. As shown on the right plot, in contrast to the untransduced T cells, CAR T cells from all conditions secrete both cytokines. The only difference between the CAR T cells generated with the short or long pre-expansion process is the increased TNF secretion following the shorter process. In summary, the shorter seed train is beneficial for CAR T cell expansion in T flasks, especially regarding the growth kinetics and the phenotype, and less pronounced for functionality. Upon showing the advantages of shortening the pre-expansion phase, we scaled up the 7-day T-cell expansion from T-flasks to the AMBER 250 bioreactor. Therefore, the CAR T-cells were cultured in a fed batch process that was based on feeding every second day by diluting with fresh media. The only differences between the two conditions are the duration of the pre-expansion as well as the number of activations. The culture in the AMBER 250 bioreactor confirmed the data obtained in T-flasks with better CAR T-cell growth upon the 3-day pre-expansion. Based on these results, we aim to investigate the impact of further process parameters on the CAR T-cell expansion in stirred tank bioreactors. And the next research question that we addressed was whether process intensification methods can lead to reduction of process time or increase of final cell yield. Therefore, we compared the fed batch process in AMBER 250 modular to a perfusion process with the AMBER 250 high throughput. To do so, we applied the design of experiment DOE approach to study a range of process parameters in the AMBER 250 to understand their impact on CAR T-cell expansion, phenotype, and function with a view to optimizing the process. The DOE methodology provides a systematic approach to study the impact of each process parameter and its concomitant effect on the other investigated parameters, thereby enabling a larger design testing space to be investigated so a more representative optimum can be identified when comparing with one factor at a time studies. In our case, an experimental space based on 32 CAR T-cell expansions in the AMBER 250 high throughput was set up with the aim to identify and optimize critical process parameters for optimized CAR T-cell growth. In our setting, two media, RPMI supplemented with serum and NutriT, a serum-free xeno-free T-cell medium, were compared. Furthermore, the impact of two perfusion parameters, mentioned here as parameter A and B, was tested. As also the donor-to-donor variability is a challenge for CAR T-cell production, the robustness of the identified process effects was tested by including T-cells that originated from 3 different healthy donors. As visualized in these two plots, one for each cell culture media, we identified 32 conditions that were tested, allowed for good coverage of the experimental space. Upon running these 32 CAR T-cell expansions, MODI was applied to analyze the data and identified the best operating window for each medium while taking the parameter A and B depicted on the X and Y axis, as well as the CAR T-cell fold expansion, visualized by color, into account. The upper line shows the contour plots of CAR T-cells isolated from the 3 different donors and expanded in RPMI supplemented with serum, and the lower line shows the contour plots of CAR T-cells from the 3 donors cultured in serum-free NutriT. These plots illustrate that there is some heterogeneity between the 3 donors and that the best operating window for the process differs between the 2 media. Hence, the optimized perfusion parameter settings identified by the software could be systemically determined for each of the respective media. Next, the impact of perfusion parameter settings on CAR T-cell growth was examined in depth. Therefore, CAR T-cell growth in both cell culture media was visualized and compared to the fed batch process, which is represented by the dotted line. These two plots illustrate the benefit of perfusion versus fed batch and highlight the importance of the perfusion parameter settings, as these determine the potential of CAR T-cell growth. This becomes especially apparent when looking at the increase from the fed batch process to the optimized perfusion process, shown in light blue with NutriT. Therefore, the CAR T-cell growth kinetics in NutriT were studied in more detail. The cell viability was above 90%, especially for the process conditions reaching good expansion rates. And the final cell count upon 7-day culture in the AMBER 250 could be increased by 4.5-fold with the optimized settings. In addition to the cell growth, the CAR T cells were characterized phenotypically by flow cytometry. As shown from the fed batch data on the previous slides, the majority of the CAR T cells are naive or central memory, and there are only minor differences between the CAR T cells expanded with different perfusion parameter settings and fed batch. However, the condition with the perfusion parameter A set to 1, shown in light blue, has slightly higher frequencies of naive T cells. Additionally, the activation marker expression was analyzed with the IQ3. These results illustrate that the CAR T cell culture in the stirred tank bioreactor system does not alter the expected biological property of the CAR T cells. CD69 and CD25 are early activation markers and are still upregulated during inoculation due to the prior activation and transduction. However, continuous 7-day culture in the AMBER 250 from inoculation to harvest results in gradual downregulation of these markers. On the contrary, HLA-DR, which is a late activation marker, is seen to be further upregulated throughout the culture period. Additionally, PD-1, LAG-3, and TIM-3 were also evaluated on the IQ3, and the pattern was identical as for the early activation markers. This confirms that culturing CAR T cells in a stirred tank bioreactor system allows for downregulation of exhaustion markers that are induced upon activation and transduction of the primary T cells in the beginning of the process. To conclude, the process intensification resulted in 4.5-fold increase of final CAR T cell yield without impacting on CAR cell phenotype. When considering the autologous setting, the optimizations allow for shortening of the process time by half. When considering the allogenic setting, the optimizations allow for increase in final cell yield. Thus, process intensification is of relevance for CAR T cell manufacturing, as it reduces the amount of media and other required reagents to produce one dose, thus decreasing the cost of goods. To conclude, I'd like to sum up the results generated within this collaboration between the University College London and Sartorius and highlight future steps. We were able to successfully expand primary T cells and CAR T cells in several stirred tank bioreactors, including the AMBER 15, AMBER 250, and the Universal 1-liter as fed batch process. I focused on the CAR T cell data generated in the AMBER 250. However, the additional data can be found in the mentioned publication. We were able to optimize the perfusion parameters based on the design of experiments approach, and by this achieve 4.5 times higher CAR T cell yields upon 7-day culture in the AMBER 250 high throughput. The harvested CAR T cells have a preferable phenotype, being mainly naive and central memory, and neither activated nor exhausted. The next logic step is the upscaling of the optimized perfusion process. In order to implement this strategy, we are applying the perfusion setup from the AMBER 250 high throughput to the universal single-use 2-liter. The CAR T cell phenotype and function will be evaluated by flow cytometry and live cell imaging, and the data will be analyzed with Geometric Studio, MODI, and SIMCA, as well as Process Insights. Following 7-day expansion in the universal with NutriT GMP media, the CAR T cells will be harvested. For this, the KSAP 400, a scalable single-use automated centrifugation system, will be applied. Upon concentration and harvest of the final CAR T cells, these will be phenotypically and functionally characterized as well as biopreserved. Therefore, CAR T cells will be either cryopreserved in Nutri-Freeze C5 and recombinant albumin, or stored at 2 to 8 degrees in NutriStore. And with this, I'd like to thank especially Kasim Rafiq from University College London, as well as his team, Pierre Springel, Tiffany Hood, and Elena Costariol. And I'd like to thank all the Turius colleagues being involved in this collaboration. And with this, I'm finishing showing my last slide for those of you who are interested in testing our cell culture media. Please reach out to your local sales representative or request a sample via scanning this QR code. Thank you for your attention, and now I'm looking forward to answering your questions.
Okay, great. And as a reminder to our audience, you can go ahead and type in your questions for our speaker now. So our first question is, what was the highest cell density reached with the perfusion process, and do you think you can reach higher cell densities?
Yeah, thank you for this question. The highest cell density reached with the tested perfusion settings in these experiments with a serum-free Nutri-T was 21 million cells per milliliter, meaning that we reached almost 5 times 10 to the 9 cells in the 250 ml bioreactor. And yes, we have achieved these high cell densities, but we think that with the applied perfusion protocol, and we are currently testing further perfusion parameter settings to increase this even further. And the DOE approach is key to fine-tune process parameters to fit into the sweet spot, and in this case, with the highest possible final CAR T-cell yield.
And our next question is, what's the next phase of your research, and how do you think you can further improve your current process?
Yeah, it would be to adapt the perfusion parameters using online monitoring of the cell densities by biomass, which is a sensor for biomass, which is a sensor for biomass determination based on capacitance, with the aim to further reduce costs for media and other supplements which are required for the CAR T-cell expansion. And the goal is to automate the expansion process as much as possible, for example, with automating feeds. And this results then in a decreased amount of manual handling steps and operator interactions, and by this minimizing the risk for errors and contamination. So it would also be to adapt perfusion using online monitoring of metabolites such as glucose and lactate by our BioPad solutions.
And our next question is, how do perfusion parameters impact T-cell exhaustion?
Yes. In this case, so we look at the exhaustion markers PD-1, TIM3, and LAG3 and their co-expression, and we could see that the perfusion parameters that we tested didn't impact on the exhaustion markers, as for all the different settings, the expression was downregulated after the 7-day culture in the amber and close to 0.
And you mentioned DOE. What is it, and what is it used for?
Yeah, this is the abbreviation for design of experiment, which is a structured way to plan and analyze experiments with the goal to interpret the cause and effect relationship. So therefore, it generates new data to create models that represent the relationship between your factor, which was in our case the perfusion parameter A and B, and the responses, which was in our case the final CAR T-cell yield. And DOE is used to gain knowledge and increase the understanding, and by this it is applied to estimate proper operating conditions or estimate the design space of a system, product, or in our case, of a process.
And our next question is the optimal RPM dependent on cell type or CD markers?
Yeah, thanks for that question. In our case, we only tested the impact of the perfusion parameters on primary T cells and primary CAR T cells from different donors. So I can also speak for T cells. It might be different for other immune cells, so that would also then need to be tested either in a DOE approach or by looking at individual markers. And on the CD markers, in this case, we only looked at the T-cell marker expression as well as differentiation and exhaustion. So this would need to be studied. And I guess, I mean, we didn't test it, but yeah, the RPM would need to be tested to set the optimum or to figure out the optimum for each cell type.
And our next question is, which step do you expect to be harder during the scale-up to 2-liter single-use bioreactor? Considering the use of fiber for perfusion, do you think the cost of process will be much higher?
1 second. I mean, which step would be the hardest for the 2-liter? I mean, either this is practical or cost related. So for the scale up, yeah, you need already with the seeding have a higher starting cell number, but we already performed the first experiments, and the cell growth also in the 2-liter bioreactor looks really good. And yes, this also increased the cost. So I think it's really important to optimize the process to have a good balance between the consumable costs of media, but also of other single-use consumables like the perfusion filters. I hope this answers the question.
All right, and what was the culture duration from thaw to harvest in the stirred tank experiments?
Yeah, so because we compared these 2 different durations of the process, in the first one it was a 7-day seed train and then going another 7 days into the bioreactor, which is then a total of 14 days. But with the shortened process, it is 3 days prior seeding and then 7 days, so 10 days in total, with then a better cell growth of the CAR T cells.
And can the proposed method be tailored for cGMP production?
Yeah, that's a good question as well. So the amber itself is non-GMP and thus recommended for process development and optimization. The outlook that I showed for the single-use universal, the current single-use universal is also non-GMP, but there's for the benchtop bioreactors, there's 2, 5, and 10-liter glass vessels which are GMP, and also in close future there will be some GMP single-use solutions.
All right, well, it looks like we're running a bit short on time, so if we don't get to your questions, we'll be passing them along to Julia, who can follow up with you directly. So please go ahead and continue to type in any questions you have, and we'll get those passed along. The last question for the webcast is, what non-invasive in-process controls or sensors, example, metabolite consumption or production, are available to track the health of the culture?
Yeah, so this depends also which culture system, but now focusing on the 2-liter universal, there's you can use an apoprobe, which is located into the vessel to detect, for example, cell density. So you have a live or an online monitoring of the cell density based on capacitance, and otherwise by the biopad solutions, there could be metabolites measured such as glucose and lactate. And also here I will get back to you with further details and answer this question also offline, because there's some more available, but also, yeah, these are the biopad solutions.
All right, well, thank you so much, Julia.
Thank you.
And thank you to our audience for joining us. The recorded version of this webcast will be available for on-demand viewing on our website, and as a registered attendee, you'll receive a follow-up email providing you with the direct link. We look forward to having you join us at future Bioprocess International Ask the Expert webcasts. Look for those announcements in your inbox. Goodbye.